Hello and welcome. My name is Bruno Klaus. I'm currently a PhD candidate at the Federal University of São Paulo, more specifically the Institute of Science and Technology located in the city of São José dos Campos. It is a pleasure to be part of Operacis 2021, and today I'll be presenting some work done by me and also my supervisor, Lilian Berton, also from the Federal University of São Paulo. And the title of our work is Optimizing Diffusion Rate and Label Reliability in a Graph-Based Semi-Supervised Classifier. Lots of words, so I've prepared a little video to show you the basic premise of our work. As you all know, in machine learning, when we do a supervised classification task, we need to use labeled data to train our model. However, usually, labeled data is very hard to obtain, it's time-consuming, it is costly. So instead, we can use lots of inexpensive unlabeled data to make up for it. The unlabeled data can reveal some hidden structure that can improve the performance of our classifiers. But if we use a purely supervised classifier, then it only sees these two labels. And this means that it completely gets it wrong because it doesn't see that context. Here you can see where the circles in yellow, where it gets it wrong. And we can do better with semi-supervised learning. In graph-based semi-supervised learning, we can create a graph from our data. So here you can see the target label matrix, the true label matrix, and you can see a huge portion of it will always be completely zero, equal to zero, because it corresponds to the unlabeled data. And y0 here is also called initial labels. Aside from the initial labels, we have the matrix W, which is known as the adjacency matrix. And what the adjacency matrix does is it tells us the weights between each of our vertices. And usually we attribute higher weight using some kind of kernel based on proximity if our data has coordinates. And also a very important matrix is the degree matrix, which you obtain if you get the row sums of our weight matrix. Usually we make the degree matrix to be diagonal. And the other very important matrix is the normalized graph Laplacian, which is the analog to what we would have to the Laplace-Beltrami operator on smooth manifolds. But here it is basically the discretized version. We use this operator for basically everything in graph-based semi-supervised learning. So what is our goal? Our goal is to produce an ideal classification matrix F, and we want it to satisfy a trade-off, minimize some cost that involves graph smoothness. It must be smooth with respect to the graph, as in local differences, and also fit the initial labels. Okay? So we use this parameter mu as sort of the trade-off here. So the classic solution is label spreading. We proceed via iteration using a step variable t. We just start with the initial labels, the non-label matrix, and then we just do this very simple convex sum using the 1 minus alpha times the initial labels plus alpha, then this kind of smoothness term on the right, because alpha will always be between 0 and 1. It will always be kind of a convex linear combination. And if this variable alpha is known as the diffusion rate. And this diffusion rate is obtained directly from the trade-off. So when alpha is very close to 1, labels spread very far. So how can we visualize the spread of those labels? Well, here you can see small spread near 0 and a big spread near 1. We can make a graph on alpha, so the x-axis is the walk length, and the y-axis is the kind of a reward on arrival. And this will kind of represent the rewards you get during a random walk, which is a very interesting interpretation. You start a random walk at a vertex, and what you want to know is, if I arrive at a labeled instance, later on in the walk, how much reward do I still get for that class? So here we can see an example. If alpha is very small, then you only get the immediate reward. So here it just messes around, and here it reaches class blue, and then it practically ignores nothing else because the decay is so drastic. It decays really, really quickly. On the other hand, if we increase the diffusion rate parameter alpha, then we increase the rewards later on. So you see what happens is, again, if we go to the random walk, we have used the same path as before. We want to know the classification for this unlabeled vertex 4. What is the class? So it goes here, it's blue for a little while, but then later on it just gets stuck here at the red vertices, and because the reward is still great, then it gets the classification as the red class. So as it turns out, label spreading also converges to a closed form solution. And here's a description of it. It's 1 minus alpha times this matrix P, which is called propagation matrix, a matrix composed with the matrix Y. Here, Y is still the initial labels. So it is what this tells us is that the final classification is just some sort of linear combination of the known initial labels. All right. So what matrix P tells us is how much does a vertex influence the other vertex, and this matrix will be unfortunately dense. And what if we set the diagonal to 0? This is the central question of our work. We get this propagation matrix and we set the diagonal to 0. So by setting the diagonal to 0, we can, for example, we can identify noisy labels. And we'll see why is that. The reason is very simple. So if we didn't do that, we already get an initial boost for the blue class if we begin at vertex 5, and if we go back through that vertex, later on the walk we receive another boost. So what happens in practice is that usually, in our baseline, the label spreading, we do not assign different classification to the labeled set, only to the unlabeled set. But if we set that to 0, we remove that diagonal, then suddenly it is as if only that label did not exist. So it can go back without a problem. It doesn't get anything from the blue class, just the red class. So as a result, we can start at label instances and use that to diagnose our labels. Alright, so the other important thing that we've discovered we can do with our approach is that by setting the diagonal to 0, we can select the best alpha. This is because, again, when we perform the random walk on a label, we zero out the diagonal, we remove the effect of the label on its final classification. So it's as if we performed leave one out validation. And that is huge, because leave one out validation is usually supposed to be very robust. However, our previous naive approach that we have published in other papers has some problems. First of all, it requires a very bad complexity for matrix inversion when we're calculating P, and moreover, P is dense. It will usually not fit into memory. And lastly, P must be recalculated for each new diffusion rate, each new alpha. So this makes it a very inefficient approach to begin with, which is expected for leave one out validation. But still, we can do better. So the eigendecomposition of the graph Laplacian is our current approach for this paper that improves space complexity and time complexity as well. So we know that Laplacian allows for an eigendecomposition. It is written as U lambda U transpose. So what's important is that each column of the matrix U corresponds to an eigenvector. Any function on the graph can be written as a linear combination of these eigenvectors, which we call eigenfunctions. And moreover, the lower eigenvalues correspond to smoothness on the graph. So the eigenvectors, eigenfunctions associated with those lower eigenvalues, they are more smooth with respect to the graph. So what we do is something called a smooth eigenbasis pursuit, where we just take the first p eigenfunctions. So we make our function smoother that way, and it also saves on space and time complexity as well. Oh, and one simple thing I forgot to mention is that those matrix U, the eigenvector matrix, well, they are unitary, which comes really handy for the derivation of our solution. What this means essentially is that U composed with a U transpose to T is equal to the identity matrix. Right, so back to the presentation, and let me tell you about our previous approach, identifying noisy labels with a transductive semi-supervised leave one out filter, named LGCLVOF. So we just assume alpha is known, which is an obvious limitation. Then we calculate a propagation submatrix, that is, a subset of the propagation matrix corresponding to interactions between labeled instances. And we can get away with this because if we look at the unlabeled instances, look at the initial labels matrix, we can see that the rows corresponding to the unlabeled instances are all 0, so they do not contribute to anything. So we can calculate this matrix efficiently with a power method for a small number of labels. And once we have that, we just zero out the diagonal and calculate the consistency of labels. But the approach for this paper here at Precis uses the graph Fourier transform, that is, the Laplacian eigendecomposition. So the thing is, you can write L Laplacian equals U lambda U transpose. And also for the identity matrix, I equals U I U transpose. And this is some sort of a change of basis, right? When we sum matrices between these two matrices in the change of basis, they remain between U and U transpose. You have a U something U transpose. And because U is unitary, we can also take powers, and we still keep the same general formula of U something something U transpose. And because the propagation matrix can be written as a power series, it turns out that we have this very nice representation in spectral format, as U lambda tilde U transpose. Well, the formula for the lambda tilde, which has diagonal entries, you can see right here. Right, 1 over 1 minus alpha times 1 plus alpha times the original lambda, original eigenvalue, okay? So what do? We just find the first few eigenfunctions, that is, we do a smooth eigenbasis pursuit, that helps with complexity. Just the first p eigenfunctions, and then we just minimize this sort of loss function. Well, we minimize with respect to this new matrix right here. It's the matrix called pi, and it contains multipliers for each label. A multiplier, for example, if the label is expected to be reliable, then the multiplier is like 1. And if it isn't, the multiplier is 0 and label is unreliable. So we just use gradient descent optimization on this pi matrix. And we also use this degree matrix right here to ensure that classification matrix always sums up to 1 in each row, okay? That usually helps. And then we just correct the noisy labels. And LGC LVOD is different. We find the optimal diffusion rate, and the only difference really is that we optimize with respect to alpha. Alpha, which again parameterizes this lambda tilde diagonal matrix. And the very nice thing is that we can pre-compute this U labeled subset transpose Y labeled subset matrix right over here. And when we want to recalculate the propagation matrix for a new alpha, we can do it with a complexity of O of P, LC, with P number of eigenfunctions, L number of labels, C number of classes. So again, very effective if we have just a small number of labels, which is expected in semi-supervised learning. And then we just use the optimal diffusion rate for classification. And alright, so what are the results? Okay, so now on to the results. We had 2 different experiments, one for label noise and another one for diffusion rate. And both of them we used the 2 datasets, isolate and MNIST. We also used 2 different loss functions, cross entropy loss and mean squared error, to see if it makes a difference. For the first experiment, we just set alpha equals 0.9 because we're just looking at the noisy labels part, and we compared the results of our approach with those of robust L1 norm methods. So what we found out for isolate is that we were very successful at the task of label diagnosis. We're superior to every L1 norm method tested and also the baseline. In spite of this, performance was nearly identical on unlabeled data when compared to the baseline, which was a bit disappointing, but maybe it indicates that labels are not useful. For this specific dataset benchmark, because we had actually a large amount of labels compared to what we usually have, and also lots of classes, and I think that multiple classes might make the problem actually easier to solve. So LGC was label spreading was surprisingly competitive with the L1 norm methods and also our approach. However, our method did have the lowest percentual decrease, and overall very competitive with the L1 norm methods. Here you can see the results. You can see the difference here, 79% against baseline, 40% for the accuracy on labeled examples, and for our own implementation of the L1 norm method here, 76%. And on the other hand, on MNIST, for example, 30% label noise, the corrected labels are 89.75% accurate, which is up significantly, since the LGC baseline only has 70% accurate label data. And the performance on unlabeled data, on the other hand, was slightly lower than the LSSC robust L1 norm method, but just slightly so, still vastly superior than our own baseline. So here you can see, when we have 15% label noise, 90.45 compared to 85% of accuracy on unlabeled examples, which is good, but not as good as the 91 instead of 90 for LSSC. And part 2 is just test how well our approach estimates the best diffusion rate, and we found out that it is successful. Here you can see if the diagonal is not removed, here in red, you can see the estimated accuracy, which is way higher than what you would expect for the sort of a small alpha, because it just uses its own label, and because of that, it overestimates how good the accuracy really is. Here in purple, you see the real accuracy. On the other hand, if we do remove the diagonal, here you can see that the estimation of the accuracy, that is the red curve right here, follows very, very closely the true accuracy. That is, if you consider the unlabeled, unknown vertices as well. So that's basically it. What does the future hold? Well, what the future holds is graph neural networks. That's all I'm going to say about it. We're going to use graph neural networks to estimate the diagonal entries. And thank you all for listening. Hope you enjoyed it. You can find us at